Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. Today's session is a continuation of our last session in which we discussed and practically saw the use of signals on the shell. Today we will see how we can send signals, ignore signals, write our own signal handlers and create signal mask for processes from within a C program. Let's start playing. Well, this is the agenda of today's session. Dear students, we saw in the previous session that we can send different signals to processes using the kill command, the job and FG commands, as well as using some key combinations from the keyboard. Let us now see how can we send different signals to processes from within a C program. The first system call that we can use for this purpose is the kill system call. There are two arguments to the kill. The first argument determines to which process or to what all processes we want to send a signal. The second argument is the signal number or name. If this second argument is 0, no signal is sent, and this is used to determine if a process still exists. Let's talk about the first argument in detail. This is mostly the PID of the process to which we want to send the signal. If it is 0, then the signal is sent to every process in the same process group as the calling process, including the calling process itself. If this first argument PID is something less than -1, then the signal is sent to every process in the process group whose PGID equals the absolute value of this argument. And if this argument PID is equal to -1, then the signal is sent to every process for which the calling process has permission to send signal, except init and itself. Well, if a process wants to send a signal to itself, it can use the raise library call. If a process for some reason wants to do a suicide, it can use the abort library call, which will make the kernel send SigAbort to the calling process and generate a code dump file. And if a process wants to wait for some signal, it can use the pause system call. This will cause the process or thread to sleep until a signal, any signal, is received that either terminates it or causes it to call a signal handler. Well, dear students, the way we can set an alarm at night to wake up in the morning for prayers, a process can also set an alarm using the alarm system call by specifying the number of seconds after which it should sound. Well, we can set multiple alarms on our mobile phones, but a process has the facility of setting only one alarm. If we set a second alarm, it will return the remaining number of seconds of the previous alarm. We will see its working on the shell soon for better understanding. Well, dear students, you all must have seen and used the sleep call in your programs, which is used to sleep for a specific number of seconds. If you want to achieve fine granularity, you can use microsleep to sleep for a specific number of microseconds, or nanosleep as well. Okay, let us move on to the Linux terminal and see all these calls practically. Okay, let me use the first program that I have written, sig1.c. A very simple program. Well, this program performs a division by 0 over here. And of course, when it do that, the operating system kernel will send it sigFPE, that is floating point error signal, and it will be terminated by generating a code file. Let's run it. sig1.c. Let me show you the code as well, so that once it execute, you can see the code. Prints two messages, and then it says floating point exception. And if I do ls, well, this code file is there. Let me remove this file and run this program again. Okay. You see, it has the operating system kernel has given SigFPE to this process, but it has not generated the core dump file, which will be the default setting at your system as well. So let us check out the setting of the core file by using the command ulimit-a, and you can see the core file size is 0 right now. The default is set to 0. Let me set it to unlimited. ulimit-c unlimited, and let me repeat the above call, and you can see the core file size is set to unlimited now. Let me run the same program again now, and this time of course it will generate a core file, and it has given you the message core dumped. And if I do ls, you can see the core file is there. Okay, that is great. That is great. It is always better that the default should be set to 0 for the core file, because this way a lot of core files will be generated, and your hard disk will fill up very soon. Let's see another example program to send a signal. Okay, so this is a very simple program, just enters in an infinite loop and display a message every 1 second. Let me compile this program, sig2.c, and let me run it. You see it is running, displaying a message every 1 second, and let me press Ctrl C. Once I send Ctrl C, this SigInt is sent to the foreground running process. Let me run it again, come up on this terminal, do ps-a and do kill. Let's pose SigInt to 2530, which is the ID of this process. Remember, this process is running over here, and now I send it a signal from this terminal, and it is gone. So we can always send signals. This is the old thing, you have seen it. Let us see the use of kill system call, and let me see the man page first. So the kill, this is the page of the kill command. Let me show you the page for the kill system call. Okay, so this system call we have already discussed is used to send any signal to any process or process group. And let me show you a program that uses this system call. Okay, so what it will do is this program will sleep for 5 seconds, and then it will use the kill system call and will send a signal to itself, and signal number 1, that is sig hub, and this line of course will not be printed. Let me do gcc sig3.c ./a.out, and it will say after 5 seconds I will get a sig hub, and there you go, it has got the sig hub. Well, pretty fine. Let me show you another program, sig4.c. Okay, so this program do a fork. It performs a fork to create a child process, and this is the code of the child process. The child process simply runs in an infinite loop and display a message every 1 second. And this is the parent code. The parent sleeps for 5 seconds and then send sigsegv to the child process, having the CPID which the parent has received over here. Okay, so once we run this program, the parent will sleep for 5 seconds. This line will be printed for 5 seconds, and then the parent will send sigsegv to this child process, and then it will print this. Okay, fine. Let me do gcc sig4.c 1 2 3 4 5, and now the child will be given SigSec and this line will be printed. I have killed my child. Bye. Now this is how we send signals to other processes from within programs. Let me show you another code, sig5.c. Okay, this uses the alarm. Let me show you the main page of alarm as well. We have seen it on the slides as well, but the alarm system call is used to set an alarm for the delivery of a signal. And whenever this time expires, this number of seconds expires, the process is sent this alarm, this signal, sig alarm. Okay. Let me show you the code again. Okay, fine. Well, this program describes actually the use of alarm. Can anyone predict its output? If yes, you can pause it and write it down on a piece of paper, and then you can fall back to the video again. Anyway, let me tell you. The first call to alarm, this one, will ensure that the kernel will send sig alarm, that is signal number 14, to this process after 205 seconds. And it will return, of course, 0, because this is the first alarm, there is no alarm set before. So this will return 0 and this will be printed I contains 0. Then it will sleep for 5 seconds and then it is going to register another alarm. It will reset the alarm to 10 seconds and the alarm call will return the remaining number of seconds of the previous alarm. So it will return 200. So J will contain 200. So this will print after alarm 10 J contains 200. Then it will sleep for 100 seconds. But after just about 10 seconds, this process will be given sig alarm and the process will terminate. Let's compile and run it. sig5.c. I contains 0 and J contains, of course, 200. Here it comes, and after now 10 seconds, this program will terminate. It will not sleep for 100 seconds. Rather, it will sleep for 100 seconds, try to sleep for 100 seconds, but after 10 seconds, sig alarm will be given to this process, and of course, it will terminate. Okay, so let us fall back to the slides again. Okay, fine. Right, dear students, we have seen and understood as to how we can send signals to processes from within a C program. It is time to see as how a process can ignore the signals, how a process can execute a signal handler of its own choice using the signal system call. Well, dear students, if being a programmer you want to change the disposition of a specific signal, you can use the signal system call. The first argument to the signal system call is the signal number, whose disposition you want to change. The second argument, this one, can be a sig ign, this constant, sig ignore, that means you want to ignore the signal. This can be sig underscore DFL, that is you want to set the disposition of this signal to the default value, or it can be a user defined function address. And it has to be a pointer to a function which returns nothing and it is passed just one argument of integer type. On success, the disposition of the calling process is changed and it returns the address of the previous signal handler for that signal number. Okay. So remember, suppose this is a piece of code where you want that if sig end is given, this handler should be executed. So you use this call and save the old handler in function pointer, and after this code is over, and let's suppose over this execution of this code, you want that the old handler should work, so you set the handler of the sig into the old handler. Okay, so that is great. Let us move on to the Linux terminal for proof of concepts. Let me move on to the directory using signal, and let me cd to ignoring signals first, and let me vim ignoring sig.c. So let's see this code. This code is going to actually ignore some signals. It's very simple. The program just call the signal system call and ignore sigint. It says I want to change the disposition of this signal to sig ignore as well as sig fpe to sig ignore, and then it enters in a while one loop and prints these messages and sleep for 2 seconds and repeat. Let us compile this program and run it. See the code. It is running in this loop. I press Ctrl C. You see it is not terminated. And let me send it sig fpe from here. To the process 2654. Remember, the process is executing over here. It is executing. And let me send this signal. It is still executing. It has not terminated. So sig fpe and sig int are ignored. Let me press Ctrl backslash, and of course sig quit will be given to this process, and it is not ignored, so it will terminate with a code dump file, of course, and you can see the code dump file is there. Let me show you the code again. So it's very simple. Whatever signal you want to ignore, you write down that signal number or signal name over here and write down the constant sig ignore. Let us try writing our own signal handler now. Handling signals. Let me show you some code. Handler 1.c. Okay, fine. Well, this program registers a signal handler for sigint. It registers a signal handler using signal system call and registers the signal handler for sigint, but this time it is not ignoring it. It is being passed a function pointer, and this is the code of that function. It just simply prints a line, and then it enters in an infinite loop. So once the process will be in this loop, whenever I will send sigint to this process, it will not terminate, rather it will execute this code. Let me compile and run this program. Okay, it is an infinite loop. Let me press Ctrl plus C. Ctrl plus C. So it is not terminating. Whenever I press Ctrl plus C, sigint is given to this process, and instead of termination, it executes the code that is there in that signal handler. And if I press Ctrl backslash, sig quit will be given, and since we don't have written any handler of sig quit, so it has terminated. Okay, let me show you some other code. Handler 2.c. Fine. Well, over here, what I'm doing is I am writing handler for sigint, writing handler for sig quit, and writing handler for sig tstp. That is, I am writing handler for all those 3 signals which can be sent via keyboard. So whenever sigint will be given, this function will be executed. When sig quit will be given, this function will be executed, and when sig tstp will be given, this function will be executed. And this is the code of the handlers. And remember, this signum, this is the actual signal number which will be sent to this handler. So once sig int will be executed, this will contain 2, and when sig quit will be executed, it will contain 3, and this will probably contain 20. The other important point to note is that once this handler will be executed once, I am again registering the sig int to default. That means when the second time sig int will be given to this process, it will terminate. I hope the code is clear. Let's check this out. It is running in the infinite loop. I have pressed Ctrl C. It says no, I'm not dying. I press Ctrl backslash. It is not dying. I'm pressing Ctrl Z. It is not being suspended. Let me press Ctrl C again. I have pressed Ctrl C again and it has terminated because over here, once this handler will be executed once, I am setting the SigInt back to the default setting. I hope this makes sense to you all. Let me show you another code. Handler 3.c. Okay, well, over here, instead of writing different functions for different handlers, I have written just one handler that will handle all these signals: SigInt, SigQuit, SigTSTP, FPEKL, and SigStop. There is just one handler, one function whose name is myHandler. And this is the code of myHandler. It receives a signal number, and using that it uses a switch case, and if the signal number contains SigInt, this will be printed. If it is 3, that means SigQuit, 20 means SigTSTP, 8 means SigFPE, and 9 means SigSkill, and 19 means SigStop. Remember, dear students, we have talked in the previous session that there are two signals which cannot be caught, which cannot be handled. They are SigKill and SigStop. You cannot catch these signals. Although I have tried to catch these two signals, but soon we will see these signals will not be caught. Whenever this process will get SigKill, it will of course terminate, although we have written its handler. Handler 3.c ./a.out. Okay, let me press Ctrl C. Let me come up over here. PS-A. Okay, now let me send sig FPE to 2759. Here is the process which is running right now, and here I am sending sig FPE, and my handler is executed. It has not terminated. Let me send the silver bullet, that is SigKill. Remember, program is running. I have written the handler for SigKill and it is not executed. The process has terminated. Hence, it proves that both the two signals, that is signal number 9, SigKill, and signal number 19, SigStop, they cannot be caught. They are non-catchable. Let me show you another code. I have prepared a lot of examples so that you can understand things properly. Okay. Can anybody tell me what is happening over here? Okay. Yes, you are right. The main function is actually registering a signal handler for SigInt, and this is the handler for SigInt, and then it is entering a while one loop, and whenever I will send SigInt to this process, this handler will be executed. Okay, fine. Whenever it will be executed, for the first time it will be executed and count will contain 1, the second time count will contain 2 and 3 and 4 and 5, and this count will keep on increasing, and once the count will reach 5, it will say this line: if you insist, do it again and I will die. So for the first 4 times this line will be printed. For the 5th time it will say do it again and I will die. And then over here you see it is setting the SigInt to the default setting. So once I press Ctrl plus C for the 6th time, this process will of course terminate. Okay, this is fun. Let's check out. Okay, so this is running the while loop. I press Ctrl C for the first time, second, third, fourth, and now when I will press it for the fifth time, it will say yes, from now on if you will press, I will die. And now the handler of SigInt has been set to default, and if I press Ctrl plus C, it terminates. That's great. That is great. Sorry. Okay, let me clear screen and show you the code for another example. Handler 5.c. Please do see this code and check out what will be the output of this code once you run it. This will give you a clear understanding of different signals and how they behave. Fine. Now let us fall back to the slides and move ahead. Fine. Let us talk about the masking of the signals now. We know how to ignore signals and how to write our own handlers. Although we have written just hello world handlers, you can write better ones. And let me see what do you mean by a process signal mask and how we can create a signal mask using the SigProcMask system call. Okay, dear students, one of the problems that might occur when handling a signal is the occurrence of a second signal while the signal handler function is being executed. Well, a process can temporarily prevent signals from being delivered by masking it while it is doing something critical or while it is executing inside a signal handler. For that purpose, every process has a signal mask that defines the set of signals currently blocked for that process. One bit for each possible signal. And if a bit is on, that signal is currently blocked. Okay, to create a process signal mask, you need to create a variable of type sigset_t. And then we have different functions that can be used to populate this variable. This function sigEmptySet, this initializes this signal set to contain no members, while this sigFillSet function initializes a set that contains all the signals. That is, all the signals are masked. Over here, no signal is masked. And this SigAddSet and SigDelSet can be used to add an individual signal to this set or remove an individual signal from this set. Normally, there are two ways to initialize a signal set. You can initially specify it to be empty with sigEmptySet, and then you can add specified signals individually using SigAddSet. Or you can initially specify it to be full with sigFillSet and then delete specified signals individually using SigDelSet. Okay, once you have created the process signal mask, you need to set that mask for that process, and for that purpose you use this call SigProcMask. That is, the SigProcMask system call allows us to get the existing signal mask or set a new signal mask of a process. This second argument specifies how the new specifies the new signal mask, and if this is null, that means you are not interested to change the signal mask. This is the third argument. This will store the old mask of the process. This may be useful when you want to restore the previous masking state once you are done executing your critical section or some handler code. Well, this first argument, how, actually determines how the process signal mask will be changed. It can have these three values: SigBlock, SigUnblock, and SigSetMask. If you use SigBlock at this place, the set of blocked signal is the union of the new set and the old set. And if you use SigUnblock over here, the signal in the new set are removed from the current set. And it is of course legal to attempt to unblock a signal which is not blocked. And we normally use SigSetMask. If you use SigSetMask over here, the set of blocked signal is a set of the argument, second argument, that is a new set. Let us move on to the terminal and see the proof of this concept so that we have very clear understanding of what do we mean by a process mask. Let me move on to the directory masking signals and let me show you the code SigProcMask 1.c. Fine. Okay, so over here on this line what I'm doing is I'm creating two variables of type SigSet_t. This is the new set and this is the old set. Then what I'm doing is I'm calling SigEmpty set on the new set. That is, all the signals are unmasked. And then I'm doing a SigAdd set. I am adding the sig into the set, that is, I'm masking the SigInt. Then I'm calling SigProcMask to set the current process mask to new set. And I've used SigSetMask, that is, the new mask should be exactly whatever is there in this sig set. And I've used a pointer to the SigSet variable old set over here to get the old mask. And then I have entered in this loop. So once the process is executing in this loop, SigInt is masked. So this loop, which will run for 10 seconds, if SigInt is sent to this process, it will not be delivered to it. It will be made pending, and after it comes out of this loop and calls this statement, that is SigProcMask, which says that set it to the old set, that signal will be immediately given to the process and the process will terminate and this line will not be executed. Once again, let me tell you, we have masked SigInt for this portion of the code. If a SigInt is delivered to the process when it is executing over here, SigInt will not be delivered to this process. It will only be delivered once we will unmask this signal. Let us run this code and see it. Let me show you the code as well. ./a.out. So this is the first loop which is running for 10 seconds. I am pressing Ctrl+C. You see, I have sent Ctrl+C. It has been masked, and as soon as the SigProcMask is set to the old set, it is delivered. So this portion, that is, this piece of code has executed in full. Although I have given the SigInt after just 1, 2, 3, 4, 5, 6, after the 6th iteration of the loop. On the contrary, if I run it like this and I don't give it a SigInt, it will execute that piece of code for 10 lines, and then the next piece of code, that is the remaining 10 lines, will also be printed, which is the old signal set. Okay, so far so good. Let's fall back to the slides. Well, dear students, the task of ignoring signals and writing signal handlers using signal system call has become obsolete and should be avoided. Better to use sigaction, which is a newer system call. This slide shows the 3 limitations of signal system call. Well, using the signal call, we cannot determine the current disposition of a signal without changing the disposition. The second limitation is, if we use signal to register a handler for a signal, it is possible that after we enter the signal handler, but before we manage to mask all the signal using SigProcMask, we may receive another signal which will be called. So using the signal call, we have a separate call to register for a signal and we have a separate call to mask. So there can be something in between them. After we register this and before we set a mask, the handler executes and the second signal is generated. And last but not the least, there are a lot of variations in the behavior of signal call across Unix implementations. So better to use the sigaction system call. Although sigaction is somewhat more complex to use than signal, however, it gives following advantages over signal. Number one, sigaction allows us to retrieve the disposition of signal without changing it. Number two, sigaction is more portable than the signal system call. Well, dear students, there are three arguments to sigaction. The first argument is the signal number that identifies the signal whose disposition we want to retrieve or maybe we want to change. This second argument, NewAct, is a pointer to a structure specifying the new disposition for the signal. It is a structure of type sigaction. If we are interested only in finding the existing disposition of the signal, we can specify null in the second argument. Otherwise, we specify a sigaction object over here. The third argument is the old act, and it is used to store information about the previous signal disposition. And if we are not interested in this information, we can always specify a null over here. Do see the main page of this call for detail. Let me see if we have the structure over here. Yes. So this slide shows you the structure of sigaction. There are three main members of this structure. The first is the handler, the function pointer. The second is the mask, and the third is the flags. The handler actually specifies the pointer to the handler function. The mask specifies the process signal mask to be set while this signal is being handled. And this SA flag field, we normally place a 0 over here, but this can be used to change the signal behavior if we want. Okay, let's move on to the slides again and check out some piece of code or some examples that will make this concept clear. Let me shift to the directory sigaction, and over here I have a program ignoring sig.c. So this will do nothing other than ignoring two signals. I have commented these two lines, and these lines are just similar to what we do using the signal call, that is ignoring sigint and ignoring sigfp. So what we do is we create a structure sigaction, and then we set its three fields. The first field is the handler, and I'm setting it to sigignore. The other field is flags, I'm setting it to 0. And the third is the mask. And over here I'm making the mask empty. That is, I'm not interested to mask any signal while these two signals are being handled. Then I'm calling sigaction, and I'm setting the disposition of sigaction to this sigaction structure, and disposition of sigfpe as well to this sigaction structure. And of course they are ignoring it. Let us run this program. So it is running. Let's press Ctrl+C. So you see I am pressing Ctrl+C and it is being ignored. I'm just pressing Ctrl+C and it is being ignored. Let me pass signal number 8 from over here. Kill-8 and ID is 2863. Remember, over here the process is running. You can see it is running, printing these messages. Let me pass sig8 as well, and you see it is still running. And if I press Control \, so sigquit will be delivered, and of course the process will terminate by generating a codenum file as well. Okay, so we have ignored a signal using sigaction. Let us write down a handler using sigaction. So this is the sample code for that. Fine, it is again simple, not much complex. See these lines. I have created the structure, the handler. This time it is not sigignore, it is the address of a function that is my handler, which is written over here. The SA flag is set to 0, and over here I have set sig empty set. Okay, that is, I am not masking anything. And then I am saying that sigaction, sigint, and over here I've written new act. Then the process enters in a while one loop. So whenever I will press Control plus C, or I will send a sigint to this process, once it will be executing this loop, it will not terminate, rather it will execute this piece of code. And what this is doing is, it will just print this line, and it will execute this loop for 10 times, and then it will print this line, and then it will fall back over here. That is great. So on sigint, it will execute this piece of code. And let me raise a question right now. What if my process is executing this piece of code, that is this handler code, and some other signal arrives? Will it terminate? Let's check this out. So it is in the main function. Let me press Control plus C. So I am there in that for 10 seconds, and let me press Control backslash. So the process has terminated. Let me show you the code again. So once I press Control plus C over here, this handler executes. And once the code of this handler is being executed, another signal comes and it is delivered to the process. I don't want any other signal to come till the time I am over here. I am executing this piece of code. Suppose this is a piece of critical section. This is a piece of code that must be executed atomically. Okay, so for that, what I need to do, I need to mask the signals. Let's suppose I want to mask all the signals. What I have done is, I've created the mask using the sigFillSet function. So this will fill up all the bits of this variable. So once this handler will be executing, all the signals will be masked. Remember, they will be masked, they will not be ignored. By masking, I mean once I come out of this, of course they will be delivered. Let's execute this program. We are right now in the main function. I press Control C. Now I'm in the signal handling function. I press Control backslash and Control backslash. You see, I have sent the signal, but it has not terminated. And once it falls back to the main function, the signals which were masked are delivered, and it says quit code dump. I hope the concept of masking of signals is clear to you. Let's fall back. Okay, that is all, dear students. I hope this was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.